I refer to intermolecular forces either being between pure substances or being between two different substances in a mixture. Hence, I may show you one molecule, and I'll say that it's a pure substance, meaning it's the intermolecular forces between the molecules we're looking at. Or I can say we're looking at a mixture of the intermolecular forces between two different molecules. We have, again, ionic forces. Those tend to be between metals and nonmetals. Instead of a metal, we could always have a polyatomic ion, such as NH4+. We could also have hydrogen bonding. This is a super powerful dipole-dipole force, where in addition, we must have a lone pair and we must have a hydrogen, which is directly attached. It's covalently bonded to either a nitrogen, oxygen, or fluorine. I do want to point out that we can have hydrogen bonding between identical molecules of a pure substance, or we can have hydrogen bonding between molecules. Dipole-dipole is when we have a overall dipole present in a molecule for a pure substance, and it can be a pure substance or it can be a mixture, and this is due to differences in electronegativity. If you're ever lost on which atom is more electronegative than the other, you want to keep in mind that all roads lead to fluorine. So if I give you a periodic table, the atom which is closer to fluorine is more electronegative. If it's a tie between oxygen and chlorine, oxygen's more electronegative than chlorine is. But generally, the closer the atom there is to fluorine on the periodic table, the more electronegative it is. And fluorine is the king of electronegativity. London forces, if all the dipoles cancel out, then we say it's automatically due to the temporary dipoles talked about in the slides. And these tend to, not always, but they tend to occur in pure hydrocarbons. But you still have to sit there and figure out whether all the individual dipoles cancel out. So let's go ahead and see general examples of this. Looking at the intermolecular forces slides. Here I have a pure substance with identical molecules. FYI, so these are molecules we're looking at. This is an example of molecules with ionic forces, which I'll go ahead and highlight up here. Notice these are between molecules of the same type. They're identical molecules. Over here we have a mixture, and that's when we have molecules of one type mixed in with molecules of another type. So going down, here we have pure substance molecules, and we're looking at identical molecules. Usually I won't give you identical molecules like that. I'll just give you one molecule by itself, and I'll say it's pure substance, so you have to visualize it next to another molecule of the same type. And this is where ionic forces occur. Keep in mind its opposite charge attraction. Ionic force has the strongest opposite charge attraction. And that's due to the positive and the negative being attracted to each other, and the positive and negative being attracted to each other. I try to give you example of functional groups with small hydrocarbons, so that way the London forces that's left over isn't competing, and you have a dominant intermolecular force. So in this case, the dominant intermolecular force is due to ionic forces. This is actually found on carboxylic acid salt molecules, and we'll talk about those later on. Right now I'll just give you the sketch. Moving on, here we have hydrogen bonding occurring and hydrogen bonding occurring. And again, we're looking at opposite charge attraction. As we go down the line, Here we have hydrogen bonding, hydrogen bonding, other examples of hydrogen bonding occurring. Again, for all three of these examples, notice you have a hydrogen attached to a nitrogen, and then you have lone pairs that are present. They may not be drawn, but you should know if they do occur or not. Also, we're focusing on whether you have a hydrogen that's directly attached. So technically, in this molecule right here, if I were to sit there and show it in condensed form, yes, there are hydrogens attached to the carbon hydrogen, but they're not directly attached to this oxygen over here. Only this hydrogen is. So please, we're only looking at specific hydrogens attached to a nitrogen, oxygen, or fluorine as we figure out if it should be classified as hydrogen bond. Let's go down over here. Here we have dipole-dipole forces. Why? Because there's a dipole, a overall dipole that's going up. And I'll just show you the overall dipole that's going up. Here there's an overall dipole that's going up. Consequently, they're attracted to each other due to partial positive, partial negative overall dipoles. And here we have a nice example of a typo. This should be considered dipole-dipole. Here we have another example of a typo, and this should be considered dipole-dipole forces right here. And then finally we have London forces on the bottom. On the right-hand side we have examples of mixtures, one substance mixed with another. And notice this could be considered ionic forces. Notice the metal-non-metal. Here we have hydrogen bonding. I have examples of this on the slide, but here I have other examples. Over here, these are all dipole-dipole forces. Careful on this one right here. Even though it shows a hydrogen to carbon and hydrogen condensed structure so you can see it better. Even though I have carbon and hydrogens present, they're not directly attached to an oxygen. So therefore, if we work out our dipoles, this is going to be overall dipole, dipole forces. So when I mix these two together, it's going to be dipole forces, and so forth. And here we have London. Usually, if I ask you to identify the dominant intermolecular force in a mixture, it will be with water or gasoline or hexane. So in this case, if this molecule is mixed in with water, this can form hydrogen bonding. I want to get down to this example right here. In this case right here, if this molecule is by itself, it would be dipole-dipole. However, the lone pairs on this molecule right here of this ether can actually hydrogen bond to the hydrogens on this water molecule. So technically, when you mix these two together, it can be hydrogen bonding. However, if this molecule was by itself, if we go back over here to the left-hand side, therefore it would be dipole-dipole. So pure substance, dipole-dipole, mixed with water, it would be hydrogen bonding. Same goes with this molecule down here. This is called a ketone. We get into that later on. Mixed with water, it's hydrogen bonding. And that concludes the intermolecular force summary for Part A of the 3-4 Part 1 slides.